bit. So let's have a look at theorem 2.5. Again, maybe calling these theorems is a bit strong. They're results about the Laplace transform. So this is the kind of function that we want to be able to take the transform on. It's a product of some function f times a Heaviside step function. And it isn't any old product. What's special about it is that both functions are evaluated at the same shifted argument. So the function f is not a function just of the variable t, but rather a function of the difference t minus a. And h is evaluated at t minus a. So this result says that the Laplace transform of this is it's a product of the regular transform of the function little f, which is a capital F of s, times e to the minus as, where capital F of s is the Laplace transform of f of t. Now notice the difference here. Capital F is the transform of f of t, just as the regular function f of t. Whereas the way f appears here in the thing you're taking the transform of is that f is evaluated at the shifted argument t minus a. So when we come to applying this result, we'll have to take careful note of that and implement that fact here. But this one property, in combination with the other properties of linearity of the transform and so on, this should be enough to allow us to take the transform of any kind of interesting switched signal function involving the Heaviside. Okay? Now we can prove this in a similar fashion to the previous one, where it was just taking the transform of a Heaviside on its own, by making use of the original definition of the Laplace transform. So whatever it is you're taking the transform of, it's the integral e to the minus st multiplied by that function. So multiplied by f of t minus a times h of t minus a dt. So that's just by the definition of the Laplace transform. Again, this, if you look through previous exam papers, you'll see from time to time this question has also been asked. Again, it's a nice application of the definition of the Laplace transform and a nice application of some basic manipulation techniques for integrals. So when we're looking at this, how are we thinking about this integral? Well, if you look at what we're trying to prove, well, we kind of know what we're trying to prove. We kind of know what we want to manipulate this to. We have to get it as the product of that exponential, e to the minus as, times the transform of f. Now that doesn't look out of the question here. What does the transform of f look like? Capital F of s, the transform of f. That looks like an integral of the exponential times f of t dt. We can't see that exactly here, but you can see all the ingredients of that here. There's an integral here, there's an exponential here, there's a function f here, and it's an integral with respect to t. But there's some slight twists in the way it's not an integral of the exponential times f of t, this is times f of t minus a. So there's some shifting of the argument going on, which we'll have to take account of. And the presence of that exponential factor in front, well, here's an exponential function, e to the minus st, and there are at least a few a's floating around. So it's maybe not that surprising that you're going to get some kind of factor like that coming in. So it looks a reasonable thing to try and prove. Remember, this is the integral of 0 to infinity e to the minus st f of t dt. That's what I mean. That integral up there, well, you don't see it exactly here, but you see it bits and pieces of it. Integral exponential f of t minus a. Okay, we want f of t, but it's not a million miles away from it. So that's what we got to push it through to be. So the first thing to do would be to deal with the presence of the Heaviside function. Remember, when you get down to it, the Heaviside function is extremely simple. It just takes two values, 0 or 1. And all you have to do to deal with it is just take account of where it's 0 and where it's 1. Remember, by definition, h of t minus a is 0 for t before a, and it's 1 for t after a. That's the definition of that function. So can we build that into the integral in a nice way? Well, yeah. Its behavior changes at a. So all we have to do is split this integral up to the bit of the integral before a and the bit of the integral after a. We'll assume here, as we would normally, that this point A is something after the beginning of the situation, after time 0. So it makes sense to split this integral up as the integral from 0 to A plus, leave some space there, plus the integral from A on to infinity. You can do that with integration, the basic property of integrals. You want to integrate some function over a large interval, you can split the interval up into subintervals and add together the remaining intervals. So here we're splitting at a because this function has two types of behavior, to the left of a and to the right of a. To the left of a, this factor h of t minus a is 0. So that kind of, that's all you really need to know for this part of the integral from 0 to a. This is like it's like a killing factor. It's equal to 0, so it just rubs everything out. You're just integrating zeros, which will amount to 0. Okay, so that's nice. Certainly, we quantify that exactly. It's exactly 0. This part here, when t is past a, as it is in this integral t is between a and infinity, so it's past a. There, the Heaviside is just taking the value of 1. Again, that's easy to deal with. We just omit it from the product, because it's just equal to 1. Okay. That wasn't too painful. The Heaviside function is gone. It's accounted for. We could just drop that first integral, because it's only equal to 0. So we just got this. I'll just write down again. To emphasize the fact that the other one's gone to nothing. That's just equal to 0. Now are we done? Are we finished? We have to show it's the transform capital F, which is the transform of little f. And we need this exponential factor at the front. If you look at what you've got this integral here. Yeah, it looks pretty much like that, except not exactly. So you're comparing this integral here to the integral at the top, which is what capital F is. It looks pretty much the same. There's some slight problems though. This integral begins at a, whereas the integral we want is one which begins at 0. And our function f is evaluated at t minus a, but we want it to just be evaluated at t, the same variable that you're integrating with respect to. So we can fix both of these by use of substitution. So there's another principle of integration is you can introduce a transformation into the integration variable. We were doing that at the beginning of the year, doing the multivariable chain rule for multivariable integrals. But if you go back, this is just a normal one-dimensional integral. Use a substitution that will give you a new variable of integration, u, and we'll let u be equal to t minus a. And this has a couple of interesting properties. So du is equal to dt, because a is just some fixed constant. Okay, so a is just a constant shift of t. That gives you this new quantity u. So they both have the same differential. And also interestingly, when when t is equal to a, remember you have to transform the limits of the integral as well. When t is equal to 0, sorry, when t is equal to a, that implies u is equal to 0. And as t goes to infinity, as it does in this integral, well, u is just t shifted by a fixed amount, so u will be going to infinity as well. So these are our new limits of integration. We're integrating from 0 to infinity. Okay, that's good, because that's what I want to see in my integral for the Laplace transform. And e to the minus s, so instead of t, I have to put u plus a. And instead of f of t, well, here I've got f of u, and dt is equal to du. Simplify this exponentials here, you can separate off the e to the minus sa, you're left with e to the minus su, f of u du. And a is a constant, s is an independent variable of t, so it's an independent variable of u. So this e to the minus sa, as far as the integral is concerned, is just a constant. So that can, by the linearity of integration, that constant can just float out to the front. Now here's another thing about integration. Fold it in the middle. I want to get them both from the same. So where we are here, compare it to this top. And this is another thing you have to be clear about with integration. The variable that's used has absolutely no meaning. The particular symbol that's used has absolutely no meaning at all. When you're saying an integral from 0 to infinity f of u du, you just mean you're integrating through every real number from 0 to infinity, getting the function f evaluated at that real number. The fact that you call it u is just pure arbitrary stylistic choice on my part. I chose to call it u here. Up here it's called t. Neither here nor there. Okay, t is just an arbitrary label for a real number, as is u here. So these two integrals here, they're exactly the same. Okay? One is expressed using the English alphabet letter T. This one's expressed using the English alphabet letter U. Makes no difference. They're still the same thing. So this is exactly e to the minus sa times capital F of s. Okay? The fact that this is in terms of u is no difference. So we get out the required result. Okay? Introducing this Heaviside step function as a factor, multiplying the similarly shifted f function, f evaluated at t minus a, that has the effect of multiplying the transform of the original unshifted function f, capital F of s is the transform of f of t, multiplying that by this factor e to the minus sa. Okay? So the size of the shift that's involved there, the location of the switch on point is encoded here as well, because here's our a property up there. Okay. So we'll have a look at some examples of that shortly. For the meantime, we might go on and do the same result about the Dirac delta. But before we leave it, any questions or queries about that? So that's an important. If you're, if that point wasn't immediately visible to you, the variable letter used for the integration is meaningless, really. It's just a pure U or T. Makes no difference. Okay, so the fact that it's e to the minus su, f of u to u here, and e to the minus st, f of t to t there, they're both exactly the same interval. That's an important point. Okay, so similarly, if we hope to be able to solve ODEs featuring the Dirac delta function, we better know how to take its Laplace transform. So that's theorem 2.6. The Laplace transform of delta of t minus a, and this is e to the minus as. Now this we give, okay, it's maybe not an amazingly rigorous argument for this, but it's kind of an informal limiting argument that we're going to give for this. Remember, this Dirac delta function is a bit funny. It's not really, strictly speaking, a function. It's more something you term a distribution. It's something that you integrate. It's an integral 1. Yeah, so we want to express delta t minus a as a limit of regular functions. Regular functions meaning things that actually are honest to goodness functions. But maybe in a limiting sense, we can express the Dirac delta function as those. Okay. So what we're going to use some step functions. If we're going to consider this function here. So it's 0 everywhere. I call this g of g sub u of t. This is defined to be 1 over u for t between a and b. 0 otherwise. Again, it's not amazingly important whether these are strict or weak inequality, what value it takes at these switching points. That isn't really all that crucial because you're integrating over it anyway, so the precise value at these individual points itself won't affect the integral. And you see what happens. Yeah, so this is like a rectangular switching function. It's got width u and height 1 over u. So as you let u go to 0, you're letting the width of the, it's got width u and height 1 over u, so it's got area 1, doesn't it? It always is area 1, no matter what the value of u is. And as you let u approach 0, the rectangle is getting narrower and narrower, but 1 over u is getting higher and higher. In the limiting sense, if you allow yourself to talk that way, it will have width 0 and height infinity, in a sense. But it always has the integral 1. So we could say, that the Dirac delta function t, delta of t minus a, so this is the infinite spike located at t equals a. We're going to say that this is the limit as u goes to 0 of gu of t. But now this kind of situation, this thing which is 0 everywhere except in an interval where it's a constant value, we can represent that easily using Heaviside step functions, okay? Just like we did in the examples we looked at this morning. So this is a limit as u goes to 0 of h of a, 1 over u. Oh, God. h over here. 1 over u times h of a minus h of a. Pull that up, sorry. The limit as u goes to 0, 1 over u, I've got my t's, h of t minus a minus h of t minus a plus u. Isn't that right? This expression h of t minus something minus h of t minus something else, that's the signal that's switched off everywhere except between these two arguments, between a and a plus u. And in that interval, this combination of Heavisides takes the value 1. So when you multiply it by 1 over u, you get it up to take the value 1 over u. And what we'll allow ourselves to say, really, this is where the argument is maybe a little bit weak. We're not kind of skirting over some technical details. We'll say that the Laplace transform of delta t minus a is equal to the limit as u goes to 0 of the Laplace transform of all of this. Okay, so delta t minus a is the limit of these functions, so we'll say it's the Laplace transform is the limit of the individual Laplace transforms. What we're doing there is we're taking an integral of a limit and we're interchanging the limiting process and the integral, which under certain circumstances we can do. But then this Laplace transform we can handle well enough because look, it's just a linear combination of Heavisides. And we already know what the Laplace transform of an individual Heaviside function is, because we just proved it a couple of theorems ago. So we're taking the limit of 1 over u times the Laplace transform of this Heaviside is e to the minus as over s. And the second one is e to the minus a plus u s over s. Yeah. Now what can we do with this? We want to figure out this limit. It's a limit as u goes to 0. So those two results are just using theorem 2.5. 2.4 about the transform of Heaviside step functions. This 1 over u is just like a constant multiple of that. But now we're faced with this limiting process of u. As u tends to 0. So anything that doesn't involve u will just be acting like a constant in terms of this limiting process. So if we can factor it out, we can push it outside the limiting process. And e to the minus as, we can get that as a factor of both terms. So it's going to be e to the minus as over s times times the limit as u goes to 0 of 1 over u. And what's left behind after you take out that factor? Well, you got a 1 here and a minus e to the minus us. But this e to the minus a plus u times s, e to the minus as can factor off, and you've just got remaining e to the minus us. Okay, so this bit is all well and good at the front. Now you've got to take the limit of this. You can't simply substitute 0. Substitute u equals 0 because you got a 1 over u bit here. Can't put in u equals 0. And here it's 1 minus, and when you put u equals 0 here, you get e to the 0, which is 1 So this bracket is 0. So this bracket is converging to 0. This bracket is converging to infinity. So you got a 0 over 0 thing. So you can't say for definite with simple substitution what that is. You would have to use some other technique, but we know a nice, so just reorganizing that slightly to this, just multiplying in the 1 over u's, writing this fraction. We got this fraction, but in the limit it tends to 0 over 0 because we can't evaluate it that way. So we can use L'Hopital's rule. L'Hopital's rule would be something you would use when you can't do any factorization to get rid of the 0 in the denominator. So we go for differentiating separately the top and bottom. So we can use L'Hopital's rule. So L'Hopital's rule, let's just hit this with L'Hopital's rule. So e to the minus as over s, you differentiate the top and bottom with respect to u. To differentiate the top with respect to u, well, it's an exponential, so it's just going to be the same exponential, which is e to the minus us. But I had a minus sign, and then we're going to have to multiply it by a minus s, so that seems to be s times e to the minus us. And you differentiate the bottom with respect to u, you just get 1. Okay, differentiate the top with respect to u, differentiate the bottom with respect to u. We got that ratio, and now there's no problem. Now we can just evaluate the limit by substituting u equals 0. So you have e to the 0, which is just 1, so you just have s. The s that you get will cancel with that s. So you just get e to the minus as required. That's what we said we would get. So that is, just at the top of the page there, that is the Laplace transform of the Dirac delta. Is that okay? Any queries? Yes. Questions? Which, here to here or here to the?
Yeah,
the last one. So the last one is, so I've got a limit of something. Limit as u goes to 0, and I can just evaluate that by substituting the limiting value u equals 0. So when you do that, you've got e to the minus 0s. So you just got e to the 0, 1. So you've just got s as the limit, and that cancels with that one to leave you e to the minus 8. Yeah. Okay. So that's good. We asked ourselves to bring these two new functions in to be able to take their Laplace transform. So we've just seen those properties there: the Laplace transform of Heaviside, Laplace transform of Heaviside multiplied by something, and the Laplace transform of the Dirac delta. So before we go on to face a Heaviside involving these, let's just do a little bit of practice with some example applications of these properties. So the first application is to take this function rt, which is t squared times h of t minus 2. Just graph that, so it's 0 everywhere until 2, and then it's the function t squared, begin at 4, and then kind of go up and up. So that's kind of roughly a graph of that function. It's equal to 0 everywhere up here, and then t equals 2, it suddenly switches on and starts taking the value t squared. Onwards and upwards. So what's the task here? Find the Laplace transform of this. what's this going to look like? So what we're tempted to do is to use property theorem 2.5. Just slip it in behind it here. See it? There on the page is theorem 2.5, the statement of it, at least at the top. So what we'd like to do is use that because it looks like it's the correct thing to use, because that allows you to take the Laplace transform of something multiplied by a Heaviside. And here, indeed, we do have something multiplied by a Heaviside. Well, we pause a little bit because the something at the front, f of t minus a, has to be expressed in that special way. It has to be expressed as a function of the same argument as the Heaviside. The argument of the Heaviside here is t minus 2, but this is just a function of t squared. We would like to re-express that polynomial bit at the front as to be a function of t minus 2 as the argument to the polynomial rather than just t. So r of t, which is t squared times h of t minus 2. So what we're going to do here is attempt to recast this in the form ready for theorem 2.5. It's not ready for theorem 2.5 at the moment because it's not a function of t minus 2 at the front. It's a function of t squared. But without too much difficulty, we can reimagine it so that it is a function of t minus 2. And what do? You take the value t minus 2, and you add 2 to it, and then you square it. Now this, when you first see this, it's a little bit confusing, but what we're just trying to do is we're trying to isolate, we're trying to see this function as how you talk about this function here as a function of t minus 2. And it's this function here where you add 2 to the argument and then you square the result. Adding the 2 to it cancels out that minus 2, and then you square it and you end up with t squared. So what we're going to do is we're going to call this g of t minus 2 times a h of t minus 2, where g of t, g is the function defined by g of t equals t plus 2 all squared, or in other words, the polynomial t squared plus 4t plus 4. Now that looks confusing because, and it is a little bit confusing, normally we don't do things like that. Normally we don't take a perfectly nice simple expression, t squared times h t minus 2, nice, easy to say, easy to write down, and kind of recast it as this g of t minus 2, where g is this long polynomial. Normally you wouldn't do that because it obscures what's going on and it's needlessly complicated. The reason we're doing it here is because the property we proved for transforming things multiplied by Heavisides requires that the function be in this form. That whatever argument the Heaviside has, the function is expressed as a function of that same argument. Okay, but here it is. We've identified. So what we've done is we've identified which function g you apply to t minus 2 to get the quantity t squared. And the answer is this function here. It's a polynomial, t squared plus 4t plus 4. Okay. So now we can apply. Now we can apply theorem 2.5 and say that the Laplace transform of r of t, which is equal to the Laplace transform of this g of t minus 2 times h of t minus 2. Now comes the application of theorem 2.5. If you look at it. So it's e to the minus as, so the a is 2 here. E to the minus 2s. Multiplied by, well, in the theorem it says multiplied by capital F, but here what that means is multiplied by capital G being the Laplace transform of this function. Not of it evaluated at t minus 2, just the Laplace transform of this straight function. So it's t squared plus 4t plus 4. So the Laplace transform, this is going to be the Laplace transform of g of t. So that's e to the minus 2s. What's this? 2 over s cubed. That's the transform of t squared. 4t, well, t transforms to 1 over s squared, and the constant 4 transforms to 4 over s. Yep, everybody happy? So that's an application. So that last that step there is using theorem 2.5. And then I can transform this polynomial just using the table. Transform of t squared plus 4 times the transform of t plus 4 times the transform of the constant 1. Okay, there's a second example there with inverse transforms, but I won't push this right up to 10 to the hour. I'll pick that up at the start of the next hour, and we'll tackle the kind of substantial example there of problem 2.13, which is to solve that Laplace transform problem involving a Heaviside. Okay, so I'll see you in a couple of hours for that extended example, and I'll probably have a second example to go with it as well.